My name is Yan Liu, and I'm also from AirCast. I'm giving this report on behalf of the whole Spectrum Earth Technic team. So what we will go through today is first we will talk about why we need Spectrum Earth, and we will talk about what is Spectrum Earth and why we are focusing on higher resolution. After we get through all the definitions, we will see the gap between the satellite captured data and the Spectrum Earth we want to build. From there, we know what's the steps we need to do from satellite captured data to Spectrum Earth. And also, this actually is an ongoing project. The key information I will give you guys today is what we've accomplished so far, and also about our next step. So first, let's talk about why we need this. So we all acknowledge that remote sensing plays a key role in decision making in these societal benefit areas. And let's take one of them to talk about how remote sensing is being used in these scenarios, and why we what we need. So let's try to see the sustainable urban development. This is a map actually of Beijing, so you can see the bird nest here, and our department is somewhere near this place. So I will use this as a study case to show, give you the following stories. So when you're talking about sustainable urban development, a couple of things you might care. So the first one is how the urban area expanding and how it's changing. Like we are building big infrastructures, buildings, and like this Olympic gym. So for if you want to look at this by using satellite data, you might need data for a couple of years, like 5 years or 3 years at least. Also, you might care about how the environment of the urban area, like a pretty park, because that matters, like you live in the urban and you care about the environment. So for that, actually you may only need a shorter time of data, but you need higher temporal frequency so you know how it's changing through the whole year. So to do this, you will need observations with continuous coverage on the spatial scale. Also, you need a continuous temporal scale as well to show you all the difference for these two aspects. So for that, let's see what is Spectrum Earth. So Spectrum Earth, let's compare it with other concepts. So first one is the real Earth, easy to understand. It's what we are living in. Beyond that, it's image Earth. It's an image, when we talk about image Earth under the remote sensing framework, we are talking about the image captured by satellite or airplane. For that, you can look at it and you can kind of guess what's going on, such as Google Earth. In above of that, if you have Spectrum Earth, which prove the spectrum, which is the unique fingerprint information of the land surface. If you look at a spectrum of a vegetation, you will have the identical reflectivities of that land cover. And if you look at the desert, you have a different reflectance characters. So for that, you actually move a step further compared to the image Earth. You know the core information of the surface. And beyond that, based on the Spectrum Earth, you can derive all the knowledge you want. Then the ultimate goal, that's the knowledge Earth. And for the spectrum Earth, we want to incorporate the data from multiple satellites here, but we want make it easier for the users. You don't need to learn all the parameters and how to process all the satellite data. So if we break down this concept, the spectrum is the core information of the surface, which can be reflected by the surface reflectance. So it need to have multiple spectrum, and if it's better, it can have multiple spatial scales and continuous time series remote sensing coverage of the remote sensing observation. And when you talk about Earth, you want a full spatial coverage and the continuous time series. And if you put those two words together, you want more than that. Not only the spectral data set, you also want analytic products, which is derived from the spectrum information, and you also need a processing platform to support all this together. So the end user don't need to spend time to learn about all the specific landsets. And with that, you can easily use the data in the application goals you want. And as what I said earlier, we are mostly focused on the technology for Dolphin satellite. So why we are focusing on higher resolution? So what's on the monitor right now is the exact same area with different spatial resolution. We have 500 meter over over Beijing, and we have 30 meter over Beijing. At the 30 meter, you still can see this is a city, and you can see what's going on here. But for the 500 meter, it's basically a blob. You don't know what's going on at all. So the low resolution cannot capture the detailed change of the Earth's surface. High resolution are what we need now. In another aspect, one is we need higher resolution. The second is we can do it right now because the satellite Earth observation is entering the higher resolution area now. We have more than 20 satellites with high resolution, and a couple of them you may know very well is the Landsat from USA, the Sentinel from ESA, and the Dolphin data is from China. And the coverage of Dolphin WFV, actually, we have a global coverage now. But we have this great opportunity and great data, but we also have great challenges. There's a lack of continuous global coverage data set at this higher resolution. First, the data amount is way bigger than the lower resolution, and it's much difficult to process. So there's a gap between what's a satellite captured and the spectrum Earth we want to build. So let's take this globe as a prototype of the spectrum Earth. So what you want is continuous spatial and temporal coverage. But what you get when you use satellites to capture is you may have cloud. So if the cloud comes, you have nothing. And also you have data from different satellites, and they have all this difference. For example, spectral difference, spatial difference, temporal difference. When you use them, the first thing is you have to learn the detailed information of the satellite you want to use, and you have to do tons of processing before you even use the data for your application goals. So from the gap, we know the steps we need to do. So the first, we have to collect all the satellite data together so we can utilize all the information we have right now. And we perform the basic correction, the geometric correction, atmospheric correction, the angular correction for each individual of them. Then we put them together 1 second, let me close this. You remove all the difference, the spectral difference, the spatial difference, then you do gap filling to get a nice data set. And based on that, you build a platform to provide the service and make it easier for the end users. So this is all a great plan. And actually there has an expert saying this will take you tens of years to finish this project. We actually only started this project for a half year, nearly 1 year now. So what I'm going to say today is what we've accomplished is we are working on the processing for the Dolphin satellites. And we all know actually both ESA and USGS, actually they've done their part on process the Landsat data and Sentinel data, and we will incorporate them in our later process later, but their process cannot meet all our needs. But what we will focus today is the Dolphin satellite. So the end users does not need to know how to process the detail of the Dolphin satellite, but we do. We need to know exactly what's going on with each satellite. So the Dolphin means high resolution, is the first of a series of high resolution optical Earth observation satellite of CNSA, which is a short for China National Space Administration. It was launched on April 26, 2013. It has 4 multispectral wide field of view cameras. It has 4 wavelengths. It has a spatial resolution of 16 meters. So it can meet our needs for a couple of applications. On above of that, we also have Dolphin 6, which is a more younger satellite, and it has similar design with Dolphin 1. And by coupling them together, we can have more observations. And all the technology we used for Dolphin 1 can apply to Dolphin 6. The most difference between Dolphin 1 and Dolphin 6 is Dolphin 6 has a wider swath. It's almost three times or 4 times of Dolphin 1. The steps we process for Dolphin 1 is first we do the basic processing, geometric correction, radiometric correction. Above that, we also do the BRDF correction. In the end, we get the processed Dolphin 1 surface reflectance. Now let's take a close look to each process. For the geometric correction, we discovered the Dolphin 1 actually is a little bit offset compared to Landsat and Sentinel. So before all the processing, we need to correct this. And right now, actually, there are a lot of tools you can do this automatically without you clicking the ground control point by yourself. For example, the NV1, but you have to use the version 5.5 above. You install the data support tools and the RPC, also rectification using a reference image batch tool in the App Store, and it will automatically generate the GPS by itself. For the input, you have to put 2 inputs. One is DEM and one is a reference image, and make sure the coverage of that is bigger than the Dolphin data, and it will correct using the RPC algorithm. This algorithm does not only perform the regular geometric correction, but it also creates a distortion due to the complex terrain, such as mountain areas. So on the bottom, this is a image showing the difference before and after the correction. we can see after this correction, actually these two images are aligned together nicely. So we know they can match together. And then you move to the radiometric correction. So there are two major steps in this part. So one is the radiometric calibration, and another one is atmospheric correction. So the first step will convert the DN value captured by the satellite to the radiance, and the atmosphere correction then converts the radiance to the land surface reflectance. To do the radiometric correction, we need to use the gain and bias coefficient number to convert the DN value to the radiance. And the radiance actually, if we look at this colored picture, is exactly what captured by the satellites. The DN value actually is just a digit number, so it does not have any meanings. After this calibration, the readings actually have physical meanings and can be used to do further processings. And the gain and bias actually is different for each satellites, and Cresta is in charge of providing this coefficient to all the users. But however, after we finish the calibration, we discovered there are difference even between different WFVs. So we can see from the picture above, the WFV1 and 2 looks kind of close, but the 3 and 4 is a little bit different than the WFV1 and 2. We are still trying to figure out what causes this difference. But our solution to deal with this problem is use one WFV as reference, and we do cross calibration. Luckily, these 4 cameras, they have overlap areas. So we use these overlap areas to the cross calibration. We know this overlap areas, they should have the same data. So we use these overlap areas to build the relationship between the different WFV. Then we can perform this to the whole image and get nice results. So here we have a before and after correction, and we can see this solution actually is working very well. We don't see the gap here anymore. After that, after we got the nice radiance, our next step is to do the atmospheric correction. So let's go back to this picture again. So what we just did is get the value directly captured by the satellite is the radiance. That's a value at the top of the atmosphere. But what we want to get actually is the real surface reflectance. So this is the bottom of the atmosphere. So here is what we want, and this actually is the core information of the surface. So to do this, we used a classic atmospheric correction code, which is called 6S. It's a basic radiation transfer code used to calibrate the lookup tables to perform the atmospheric correction. The input data, you need to provide the atmosphere parameters, including aerosol optical depths, the viewing geometry, the elevation, and so on. And it will automatically generate the equation that you can use to calculate your surface reflectance. And you apply that equation and you get your surface reflectance. The next step is we do a BRDF correction. And I actually spent a couple more slides here to explain what's BRDF. So what is BRDF? BRDF is bidirectional reflectance distribution function. It describes the reflectivity character of the surface, and this is basically determined by the surface itself. So the ideal situation is the Lambertian reflectance, which means you get exact same value no matter where you are looking at the objects. But in real life, actually most objects are bidirectional reflectance. Let's see the bidirectional reflectance in remote sensing images. So if we zoom in a satellite pixel, in each pixel, if we zoom in a pixel in forest, you will have this these trees in this pixel. But when you capture by satellite, it's only one pixel and one value. But if you look in, you will see this pixel actually contains different informations. It has the bright side of the tree, the bright side of the ground, and it also has the shadowed area of the tree and shadow area of the ground. So if you look from the different angles, if you look from the angle of the sun, you will see more bright information. And if you look at opposite side, you will get darker information. And we can see this from the real life. You do get different values even when you are looking at the exact same thing. So angles are very important, and before you do further processing, you also need to remove this as well. So the BRDF correction here, we use the kernel-driven model. It uses the linear combination of kernels with certain physical meanings to describe the bidirectional reflectance of the surface area. So it contains three parts. The first part is the isotropic parameter. It basically derives how bright the surface is. It also has the volumetric parameter. It describes how the volumetric scattering of the surface, and it also has the geometric parameter, describes the geometric scattering of the surface. And with this equation, you basically can estimate reflectance at any desired angle. We need to use the priority knowledge to help us to perform the BRDF correction. The product we use here is called MCD43A1. It contains all the parameters we need and with a lower spatial resolution. What we do right now is we use the dominant BRDF of the region as a priority knowledge, and we use that knowledge to calculate the reflectance at the nadir view. Then we also calculate the reflectance of the view at the same viewing of Gaufen, and we get a ratio there, and we perform the correction to get a Gaufen nadir viewed reflectance. This is a picture showing before. This is a picture of the difference before and after the BRDF correction, and we can see the difference could reach to 0.03. You may think it's not big, but actually it will reach 10% of what you are seeing on the ground. So this is the picture of Nepal, and we'll process the data from March to April of 2015. So we did get some good first results, but we still can see here it's still we can still see it's different swaths. So the major difference contributing in here is the temporal changes. And in the next step, that's what we will working on. So our next step is further to work on our technology on the golfing data to make it better. And with that, we will move on to combining all the different satellite together to get better results. And among this processing, our research actually going back and forward, trying to get the best solution. So right now, a couple of key things on top of our team's head, and I want to share with you is uh, we are still testing at which level of product to perform the cross calibration will be better. So if we can perform at DN value, at the readings value, at the readings level, or we do the calibration after we get the surface reflectance. So we are still doing a couple of tests and trying to find the best solution. And the second problem we are working on is we need to perform cloud detection to golfing data. And this is a little bit difficult because we only have 4 bands. And 4 bands to do cloud detection, that is one big challenge. And above that, if we get a good cloud detection, is how we use the images that are partially covered by cloud to do the gap filling. So this actually goes 2 directions. One is how we can use the partially covered cloud to do gap filling for other time. Another is how we fill these values, the missing values that is caused by the cloud. So unfortunately, this is the still ongoing project. So we may not have an entire Earth to share with you yet, but we have hope. We have hope, and we hope we can share it with you in a short time. And thank you. And that's all my slides.
Okay.